Alright, so today we're going to do a quick demo of our three learning algorithms and our testing class. So first up is BFS. Now all three of these were adapted from the examples we saw in class and the examples we did for the coding homework. So I won't be going into that much depth. But for BFS, the main two things, besides of course the class that fetches successor states and the implementation of the actual BFS, are these two classes. One is meaningful state. Currently, the way the cubing.py is set up, it holds as a current state a bunch of references to objects, because our cube is a bunch of objects. It's a bunch of blocks and colored squares. So to make it something readable, I took that state and then I added, not added, from it I took the block position and the block rotation. So where the individual piece of the cube is at a given time and if it's rotated at all. And along with this, just is kind of like our check of terminal, or a terminal state checker, and it just checks if a cube that has undergone all the actions currently within our action list, if it'll reach its goal state, since all cubes have the same goal state. So now we'll do a quick run, and our cube method can take in any number of things for a scramble. It could take in an integer for a random scramble. You could take in an array of strings like this for a list of moves, or even a file. So just running this, let's see, we see it output. Now this might take a couple seconds. But here we have all the different permutations and actions that it's taking as it's taking it. We just have to sit and wait for it to find the correct combination of moves to get it back to a solved state. Now what is also interesting about this program is there's a implemented kind of get debug cube. So this debug cube is kind of a sliced, flipped out version of our cube, so you can visually see the transformation that the cube will undergo. Alright, so here we have it post BFS. As you can see, it's clearly solved. All the colors are on their individual sides. And then, as you saw it scrolling down, the different permutations we took. But if we scroll all the way up, we can see the position that it starts with one right prime, which would be a counterclockwise right side rotation. Alright, now we're going to move on and we're going to look at DFS. So looking at DFS, we are going to, again, very similar thing, very similar to BFS. The only difference, of course, is how the fringe is implemented. But as I said before, it's based off the implementation of the homework in class. So for brevity, I'm not going to go through that, and I will point again to these two classes, which are the same as before. So we're going to run DFS now with a just clockwise down rotation. Alright, now that one was marginally quicker, and you can see just one down rotation. So this is the scrambled cube, this is during DFS actions taken, and this is post DFS. Okay, now we're going to move on to the reflex agent. Now this one is interesting, so I will talk more about this one and just look at a couple things. Again, I'm not going to show you the main program, but we will look at, here's our evaluation function. Now originally, we looked at doing the distance, so how far away each piece of the cube, each block, was from its final position, and how close the rotation was. But instead of that, we ended up going with looking at the individual colored squares, so all these individual colors on the cube, and seeing if they're on the correct side or in the correct position. Now, there are some limitations to this, which I'll discuss in a minute after we get a good example of this running through. That was really quick. And we can see this is our score for evaluation, and just a D prime. But to discuss really quick about some limitations of this, anyone who's ever tried to solve a Rubik's Cube, you know that just because one side of it may be fully solved doesn't mean the cube itself is close to being finished. So this is not the most, so using this, it's not the most accurate representation of a good evaluation function. It's good for very low scramble numbers, it'll work, but for high scramble numbers, this could just lead it to making moves to infinity, essentially. And with further testing, I'm confident we could pin down a more broad and appropriate evaluation function. So speaking of testing, we're going to go look at our testing.py. And this program was used to test all of the algorithms. Now, essentially, it outputs just some primary information about what round it's going on, and it takes in a scramble length for the number of times you want it to be run. Now, they all work off the same cubes. That's where the cube is built. Here they're wrapped in this try-catch block. This is due to calling this function timeout, which essentially prevents any of these runtimes from going over 10 minutes. That way you're not sitting here forever waiting for these to finish. And it's going to output a list of moves and how long it takes using these counters. So we're going to run it for one scramble length, 10 rounds. Alright. That's going to take a while, but as you can see, it just runs the programs as we saw before. And it's going to run all of them one after another for the specified number of rounds, in this case 10. Now, I won't bore you with having to sit here and sit through all of these different permutations, because it may take a while. If you look into the experimental results, you can see some different times and some interesting observations that were gained from it. So there we go. So as you can see, the BFS algorithm tends to run the longest. So after that's done, DFS and the reflex agent seem to run very quickly in comparison. So it will look like a lot of numbers, or not numbers, a lot of letters, and then it will suddenly shoot up and have some spaces as the other ones start to run, and then they'll output those relatively quickly and advance the round. Now, I said before, I won't sit here as we get to round 2 and make us sit through all 10 rounds, so this now ends the demo.